Hello everyone, welcome to the video on antenna and microwave engineering. In this first video, we are going to see the introductory topic of Unit 1, which is Introduction to Microwave Systems and Antennas. So let us first see the outline of this presentation and the upcoming presentations. So we are going to see these concepts in the basics of antenna. So the first one, in this first video, we will see the physical concept of radiation. That is, we will see how radiation is created using an antenna. And the next video we will concentrate on, once the radiation is created, we can classify the regions of radiation as near field and far field. That will be focused in the second video. The third video we will see in the radiation pattern that we are going to draw, what are the various characteristics of the pattern that we draw from the radiation. That is the third video all about. And in the final video, we will see various parameters of the antenna. So any device has a set of parameters. Similarly, we will see the parameters of the antenna such as directivity, antenna gain, radiation efficiency, radiation intensity, antenna efficiency, and so on. So no need to confuse about all that. We will first start with what is an antenna and how antenna produces radiation. So let us start with the introduction on what is an antenna. So antenna is a very common device that we see in and around us in our day-to-day lives. Starting from our mobile phones, televisions, on the rooftops we can see the dish antennas. Each and every device that we use and exists around us contain antennas. But we have never thought how a particular signal is transmitted by an antenna or it is received by an antenna. And why antenna is designed in such a way. Certain antennas are extremely small, certain antennas are very large. What is the reason for all those? So that is what this total subject is going to concentrate on. So let us first start by defining what the term antenna means. So you can see here the basic definitions of what is an antenna. So an antenna or aerial is considered as a region of transition between a transmission line and space. In the previous semester, we have studied the subject transmission lines and RF systems. And the transmission line, what we studied is a form of a guided communication, which means a closed path where we can predict the starting point and the ending point. So transmission line is a form of a guided communication, but we cannot say always the devices that we use are wired in nature. It is not guided in nature. Your mobile communication is an unguided form, which means the waves are traveling in free space. So which means the waves that are transmitting through the transmission line, it has to be transferred, or we can say there must be a transition from a guided form to an unguided structure. That is where antenna comes into play. So if you see this diagram, this clearly says from this part to this part. So we can see that from this part to this part it is a transmission line, and this here it is free space, which means the radiations are in air. But between the transmission line and the free space we need some transition medium that can transfer the guided waves into unguided waves, and that is where we have some devices called as antennas. And why have we drawn antennas to be of this structure? If you see here, it is tapered in nature. Tapered means it is somewhat discontinuous. If you see the transmission line, it is a form of a straight line. The conductor is straight. But when we have drawn an antenna, we have drawn it tapered in form. The reason for that we will see in the upcoming topics. So we can say that one of the definition that holds true for an antenna is it is a region of transition between a guided form, which is the transmission line, and the free space propagation, which is unguided in nature, right? And similarly at the receiver side, it has to convert back the plane waves, the E lines or the electric field lines, which is again from free space back to the transmission line. So the transmission line, once again, as we saw in our previous semester subject, it is capable of guiding TEM waves. So it has to convert back the E lines back into the waveforms supported by the transmission lines, and it has to reach the receiver. So the antenna acts as a transition in the source side, as well as we have the antenna at the receiver side, right? So this is how we transfer energy from one point to another point through free space, because transmission lines are not capable of transmitting energy in free space. They are only guided structures. We come to the concept of antennas which transmit electromagnetic energy in free space. That is the meaning of the first definition. The second definition of what an antenna can be. So antennas radiate or direct electromagnetic energy in the desired direction. So we cannot always say that an antenna transmits in all direction. If you use your mobile phones, we do not know from which direction the radiation is coming, because I might move from one base station to another. I might receive signal from my nearest base station, so we cannot predict from where my mobile signal is coming. Whereas if you take the dish antennas on top of your home, so we have something in the form of a parabola, and to this we have some device that is connected. So this is the structure of the dish antenna on top, but this is a directed antenna. It receives signal only in the particular direction. That is why we say when the direction of the dish antenna is changed, the signal will not be properly received. Only if we go and change the direction of the antenna, we will get a proper signal, and the television will be able to view our picture. So we can also define an antenna to be it radiates or directs electromagnetic energy in the desired direction also. So it is not only it radiates energy in all directions, we can also design antennas that can transmit energy or receive energy in one particular direction. And the third thing of what an antenna might be. So as I said before, it might be isotropic in nature or anisotropic in nature. So isotropic means there is no particular direction. We can receive the signals or send the signals in any direction, and anisotropic means it is a directional antenna where direction plays a very important role in receiving energy from the other end. So all these define what an antenna is. So to just give a small recap, we can call the antenna as a transition medium from a guided line, which is a transmission line, into a free space propagation. This is what we call to be an antenna. But these are not the restrictions of what an antenna might be. There are much more definitions of what is an antenna. So if you see here, there are lot many definitions of what an antenna is. An antenna is defined as a metallic device, usually as a rod or wire, for radiating or receiving radio waves. So initially when they found antenna back in 1960s and 1860s, before and all, antenna was usually considered to be a metal. So initially the signals was transmitted and received only using metallic devices. That was how the antenna evolution started. But as years passed on, it was not only restricted to metals, but they found that inventions were started that not only metallic devices but non-metallic devices can also radiate electromagnetic waves. So starting from the definition of a metallic device that receives or radiates radio waves, we came to a more enhanced definition as it is a means for radiating or receiving radio waves. In this definition, the term metallic is not there, which means it is not only restricted to metallic devices. It is not that only metals can radiate or receive radio waves. Non-metallic devices were also capable of transmitting and receiving radio waves. And this definition was formulated by the IEEE in the year 1983. And this is the definition that we saw already. It is a transitional structure between the free space and a guiding device. And this guiding device is nothing but the transmission line that we see here, that is straight in nature. And this transmission line, this might be a coaxial cable, or it might also be a waveguide when we go for very high frequency transmissions, right? So this diagram depicts the transition. It is similar to the previous diagram. So we have a source. So this part is the source, which is going to act as a supplier of energy, and after this we have a transmission line through which my waves are going to travel, and if these waves has to be radiated into free space, we need some transitional device in between, which is nothing but our antenna, right? So this is the diagram that depicts how the waves get transmitted from a guided device into your free space propagation. And this diagram is for a parabolic reflector on top of our home. So as I told here, you would have seen a parabolic dish, and some device there will be a projection on top of the parabolic dish. This device is that. So this device will accept the incoming radio waves, and it is going to take only the E field. So here it is going to take up only the electric field, which is nothing but voltage, and that voltage will be given to your television through which we see our pictures. So this acts as an antenna for the parabolic dish on the top of our homes, which receives the incoming signals, and it gives the specific voltage values to your television or any device that is connected where we see the pictures that gets displayed. So these are the definitions that have been described for an antenna. Now, we said that antenna is a transition device. It is going to transfer the wave from a guided structure into a free space propagation. So to bring a much more clarity of this, we will try drawing a Thevenin equivalent of the transmission line of an antenna. So this is actually in the transmitting side. We have a source here. This VG represents, this is the source for us. And this is the source impedance, which we represented as ZG. And at the receiver side, we have here, at the other end of the transmission line, we see that we have an antenna which is used for translating the guided waves into unguided waves. And we have two resistors here. It is RL and RR, and reactance value XA. RL stands for the loss resistance, because this transmission line can be a conductor, or it can be a dielectric, or it might be a combination of those two also. So in that cases, definitely some losses will be present in your circuit. We cannot say that 100% conductance will be there. So for that we represent RL, which is the loss resistance. RR stands for the radiation resistance, and this is a very important term as far as antenna is concerned. The radiation resistance is what defines the amount of radiation that has been produced by the antenna. And together all these three elements RL, RR and XA together gives your antenna impedance, which is ZA. So these two are in series, so it becomes RL plus RR, and the imaginary part is plus JXA. So the combination of RL plus RR plus JXA gives our antenna impedance ZA. And when can we say that maximum power gets transferred from the source to the antenna? As per maximum power transfer theorem, only if the source impedance and the antenna impedance are matched in nature, we can say that maximum power gets transferred from here to here. Now what happens if proper matching has not been done? In some cases, when antenna here is not properly designed, this might lead to reflection back. So the waves will be reflected back, and which are termed as the standing waves in your transmission line. So if the antenna is improperly designed and the reflection keeps on increasing more and more, then standing wave gets created within your transmission line. At this point, what happens? The transmission line, it becomes as a storage element where voltage keeps on accumulating instead of guiding energy from the transmission line to the antenna. So we have to ensure that this antenna is properly designed such that the standing waves are minimized and antenna is capable of radiating energy in a proper manner. So choosing this RL, RR and XA is an important factor, because this is what decides whether the wave is reflected back or the wave is radiated from the antenna device that is present here, right? I hope you're clear with what I've told. Now, let us see the radiation mechanism through a single wire and in case of two wires. Now, if you see any wire, a conducting wire is usually characterized by two main things. One is motion of electric charges, and because of the motion of charges, what happens? Current is created. So the motion of charge creates a current flow, and this is the main characteristic of a conducting wire. Now let us consider this conducting wire. So we are considering a single wire which has a volume charge density. So I'm going to take this Q. It is not given in the diagram. Let us take QV to be the volume charge density, which is distributed over this particular area. Now we are going to define the current density of this particular wire. If we take a small cross-sectional area, then over this cross-section, we can define the current density as Jz is equal to Qv into Vz. This Z, the suffix Z is present here because we are considering the wire to be placed along the Z plane, and it is in this direction that there is flow of current. So Jz, the current density, will be equal to Qv, which is the charge which is present there, and Vz represents the velocity of the current flow in the Z direction. So current density is given by the charge into the corresponding velocity. The charge is given by Qv, and the velocity in the Z direction is given by Vz. Now, if you consider the wire to be made of an ideal conductor, which is where there are almost zero loss, there are no losses at all, then we can consider that the charge mainly resides on the surface of the wire, which is the external area of the wire. So we're going to replace this term QV rather than representing through the volume which is considered here, through the cross-sectional part which is considered here. We can define the charge to be residing on the surface of the wire. So we change the term Jz to Js, representing that the charge density on the surface, and Qv to Qs, once again representing the charge on the surface of the wire, and it travels with the same velocity Vz, where V is the velocity in the Z direction. Now, if you assume the wire to be almost of zero radius, if the thickness is very small, if the radius of wire is almost zero, then we can directly define the current through the wire, then defining the current density. So density we say when there is an area of the wire, when the radius is large. But when I consider the radius to be very small, then we can consider it to be I instead of J. So Iz can be written as QL into Vz. Vz, as we saw earlier, it is the velocity through the Z direction, since the wire is placed in the Z direction, and QL represents it is the charge per unit length. So since there is no more concept of area, since we assumed it to be of a zero radius, we no longer talk of area, we talk only of the length L of the wire. So the length L of the wire, the charge through the length L is QL, and Vz represents the velocity with which the current is flowing through this particular wire, and that is given by the current Iz. Now what are the conditions for radiation to be created? So to create a radiation, there must be a time varying current or acceleration or deceleration. So which means there are three conditions under which radiation can be created. The first thing, either the current has to be time varying nature, or the charges has to be accelerated, or the charges has to be decelerated. So under all these three conditions, we can say that radiation can be created. Now we can actually apply the time varying characteristics to this particular equation. For example, let me have this as equation 1. So we have considered this wire to be of zero radius, which means it is a wire. Still it is a wire. So whatever conclusion I can apply to this zero radius wire, it can be expanded and applied to any other single wires also. So whatever conclusions apply to this particular equation, It holds true for this equation also. It holds true for this equation also. So therefore, we are going to differentiate this with respect to time, because what we require is a time varying current. So if I differentiate with respect to time, what happens? We get, it is variation of current. So it is diz with respect to time. So it is dt. That will be equal to ql is the charge through the length of the wire, and velocity is going to be varied because velocity keeps moving. So it is dvz divided by dt. So we are varying this equation with respect to time, and we have arrived at this particular equation. Now if L is the length of the wire, then we'll multiply this by L for both the sides. So this L into diz by dt is equal to L qL dvz by dt. And what is variation of velocity with respect to time? That is nothing but acceleration. So we can write this as L into qL into acceleration, and the direction of propagation is z direction. That is how we arrive at this particular equation. So whatever conclusion we apply to this particular equation of zero radius, the same conclusion applies to all other equations also. So this first condition we have established here. There must be a time varying current. So diz by dt represents, that is variation of current with respect to time. Right. Now we consider a single wire. So we are going to check conditions where the radiation is created, or how we can create an acceleration or deceleration. Now if a charge has to accelerate or decelerate, there must be some change in shape. So you can consider the water pipe as an example. So we have a water pipe here. So if you have a tap here, what we can say? So let me assume a tap. The water comes as a constant speed, and when I open the tap, the water rushes out of this tap, which means the flow gets accelerated, comes at a much force, a higher force. So here there will be some change. There is an increase in velocity, so we call it to be acceleration. Or if you have a same water pipe which is bent upward, we can say that the flow will become smaller, so which means it is decelerated here. So either it has to come downward to create acceleration, or it has to go upward to create deceleration, which means if my given wire is curved, so if you see here, there is a bend and there is a curve here. So either it has to be curved or it has to be bent, or if we have a difference in shape, if there is a discontinuous structure like this, here too we can create a radiation. Or if we abruptly end our particular wire, we can once again say that a radiation is created. Now let us see here. If the charge is not moving, the current is not created and there is no radiation. So only when charges move, what is current? Current is nothing but movement of charges, movement of electrons. So if the electrons do not move, then we can say that there is no current. So which means there will obviously be no radiation. The next point is if charge is moving with a uniform velocity. Now we have a wire, it is going to move through the wire with uniform velocity. So if it keeps on moving straight, like in this water pipe, 1 second there is not going to be any radiation. But to the same water pipe, if I am going to have a downward bend or an upward bend or any such type of a curve, then we can say that a radiation will be created, right? So same water pipe, as long as this is straight, the charges will keep on moving with the same uniform velocity. If to the water pipe I introduce a bend either downward, or to the water pipe I introduce a bend upward, we can say that due to change in shape, due to a bend or curve that is present here, this will try to rush through this particular bend, and because of this, radiation is created. This is your second case for which radiation might be created. The third case, if the charge is oscillating in time motion, it radiates even if the wire is straight. So we might consider the same wire, but if we give charges that are by itself oscillating in nature, then that again creates radiation even if the wire that we consider is going to be straight in nature. So these are the conditions under which we can introduce radiation. The first one, If the wire is going to be just straight without any movement of charges, there will not be radiation. Next, if the charge is going to move with uniform velocity, but if the wire is straight, once again there will not be any radiation. But if the wire is straight and we have a bend or a curve or some discontinuity or some termination, in that case a radiation will be initiated. And the fourth case, even if the wire is straight but the charge itself is oscillating in time, then we can say that a radiation will be created. Now let us see a two-wire case, which is the transmission line that we are very much familiar. So we can see that this is the transmission line that we consider and this is an antenna that we are considering. Now the electric field lines drawn between the two conductors exhibit the distribution of charge. So if you see here this transmission line, for example, consider this conductor. Movement of charges is nothing but current. So current is nothing but the electric charges. So within the transmission line, we are drawing the electrical lines of force. Now as per Maxwell's theory, always a time varying electric field creates a magnetic field. A time varying magnetic field creates an electric field. That is the concept that we are going to use here. So when this charge is time varying nature, that automatically creates a magnetic lines of force around these electric lines. Magnetic lines, physically they do not exist, but when a current carrying conductors are present, because of the movement of charges through the conductor, magnetic lines of force will be created in form of loops around the current carrying conductors. That is the mechanism that we will be following in the transmission lines and in two wire cases. So when we have a source here and because of this source electric charges are moving, this moment of charges creates a magnetic line that encircles this given conductor, right? So this is what we consider about electric lines. Now how should these electric lines be converted to free space lines? That is our next point of interest. Now, so if you see the first diagram, it shows the antenna and electric field lines. So these electric field lines will be alternating in nature. And this diagram represents the electric field lines and the antenna. Now this second diagram represents antenna and free space waves. Now how can we create these free space waves from the electric field that is generated here? Now what we can do is, if you remove this part of the antenna structure as shown here, if you see the first diagram and the second diagram, we have removed a part of the antenna structure as in the first diagram. When we remove a part of the antenna structure, then we can say that free space waves will be created. This is because of the disturbance that we create in the antenna structure that the free space waves are created, and this starts your radiation mechanism. So this is how we can produce radiations in a two-wire case. Now, we can correlate this radiation produced to water waves. So I hope most of us would have seen the waves in water, the ripples created in a water. If we drop a pebble into the water, we can see that this kind of a circling pattern is created which moves in the outward direction. So this wave, once I drop the pebble at the center, we can say that the waves travel in the outward direction. Now even after the pebble has been dropped, the disturbance is over, the waves still keep on moving outward because of the disturbance created initially, right? So I drop a pebble, because of that we can see that water waves start moving in the outward direction. Even after we finish dropping the pebble, we can say that waves keeps on traveling in the outward direction. So this is an example of radiation. Now we have a transmission line. So we have a source here. I have a transmission line. We have an antenna here. So because of the source, this is going to be my electrical disturbance that I give. So because of the source that is present here, some disturbance is created, and because of this, free space waves are created in an outward direction from the transmitting antenna. Now if I remove the source also, what happens? This keeps moving in free space to the required destination point. This is similar to the water waves. Now even if I keep, so once the first pebble is over, I keep on dropping the next pebble and the next pebble and next pebble, we can say that the water waves keeps on radiating outwards and outwards and outwards. So similarly, if I keep on giving a source to the transmission line, the radiation keeps transmitting through the free space from the transmitting antenna. So as how a pebble serves as a disturbance to the water waves, the free space radiation in antenna can be created because of the disturbance given by this source, which acts as an electrical disturbances. So radiations which are electromagnetic waves, they can be created due to electrical disturbances which is the source present at our transmission end. So hope you're clear with how a radiation is created in an antenna. So we should either have a discontinuity, a curve, or a bend or some termination to create a radiation, and also as long as a source is present, or even if initially we have a source and then we remove a source also, the waves keep on radiating to the destination as similar to how waves are created in water when we drop a pebble. So hope I've made the concept clear on how radiations are caused.